On August 12, 2026, at Plattsburgh International Airport in upstate New York, a massive prototype aircraft rolled down the runway and climbed to 1,100 feet. The test flight lasted exactly 27 minutes. That entire 27-minute trip cost exactly $5 in electricity. The Heart Aerospace X1 has a 106-foot wingspan and a takeoff weight exceeding 25,000 pounds, roughly the size of a standard regional commercial jet. To lift that mass, it relies on 4 wing-mounted electric motors, pushing a combined 1 megawatt of power. Those physical dimensions and power requirements put the X1 in a class of its own. It holds the record as the largest battery electric aircraft ever flown. Yet, if you look inside that massive fuselage, you'll find a surprising detail. There are 0 passenger seats. A pure electric system at this scale is heavily limited by weight. Adding a full payload of passengers and luggage would shorten the range so much that the plane could barely leave the airport area. Because of these physical constraints, the X1 operates strictly under an FAA experimental certificate. It will never sell a single commercial ticket. Heart Aerospace designed the X1 as a disposable flying laboratory, a tool to prove that an airliner-sized airframe can fly on battery power alone before the project is retired. Before you can build a fleet of commercial electric planes, you need real-world data. Heart Aerospace built a full-scale physical demonstrator to see how a heavy electric airframe handles taxiing, aerodynamics, and takeoff physics outside of a computer simulation. The data they collected points directly to the core bottleneck in electric aviation. Today's battery technology is incredibly heavy and lacks the energy density of jet fuel. This diagram illustrates the physics problem. If you load an aircraft with enough batteries to fly standard commercial distances, the weight of those batteries leaves almost 0 capacity for 30 passengers and their luggage. To make commercial electric flight viable today, aerospace engineers have to accept the limits of chemistry. They are abandoning the idea of a pure electric airliner in favor of a practical hybrid compromise. That compromise is the ES-30. This is the actual 30-seat production aircraft that all of the X1's test data is paving the way for. Instead of relying solely on batteries, the ES-30 uses a hybrid architecture. It pairs a heavy-duty battery system with 2 turbogenerators that run on sustainable aviation fuel. This map shows how the dual system works. For short hops, the ES-30 can fly 200 kilometers, or 125 miles, entirely on electric battery power. By engaging the turbogenerators mid-flight to supplement the batteries, the aircraft's range quadruples to 800 kilometers, covering standard regional airline routes. To build power systems that handle this specific workload, Heart Aerospace partnered with BAE Systems, a contractor with decades of experience electrifying heavy industrial vehicles. This hybrid setup balances clean energy ambitions with the strict physical realities of commercial weight limits, acting as a necessary bridge for the industry. Over the last decade, airlines have been abandoning short-haul regional flights. The older, traditional aircraft used for these routes have become far too expensive to operate and maintain. The ES-30 is designed to reverse that trend with a specific economic weapon, a projected 40% reduction in total operating costs. This saving stems from energy costs that represent a tiny fraction of jet fuel, combined with electric motors that require fewer maintenance hours than complex turbine engines. The aviation industry is backing this math with real capital. Major global carriers, including United Airlines and Air Canada, have already placed financial commitments for the ES-30. For these airlines, the ES-30 is a financial tool. It allows them to take abandoned, unprofitable regional routes and make them lucrative once again. The immediate next phase is currently underway. Heart Aerospace is actively constructing the first pre-production ES-30 at a pilot manufacturing plant in Los Angeles. The company expects to have that airframe complete and ready to initiate actual flight tests by 2028. If those tests succeed, they project a 2031 deadline to achieve FAA certification and enter active commercial passenger service. The X1's record-breaking $5 flight served as a necessary catalyst, proving the core technology required to trigger a multi-billion-dollar shift in airline economics.